Right, now the next thing we need to look at in our review of AS Kinetics is the Maxwell-Boltzmann distribution curves. Now these course candidates quite a few issues when they were doing Chem 2, and the reason for this is that students don't often know what the purpose of this curve is. Now essentially this curve is to show how the energy is distributed within a system. By a system I mean a beaker, it might be a gas vessel in an industrial reactor. A system is just a phrase that we use to represent a chemical reaction, or a container containing particles, for example. So in this particular one, what we can see is that the particle energy is distributed on the x-axis and the number of particles is shown on the y-axis. Now, as you can see, it shows that, for example, at an energy of 0, there are no particles in the system that have 0 energy. If we go along a bit, although this curve isn't numbered, it's showing me that the more particles have this energy down here than any other, because, as you can see, that's the one with the largest number of particles. So we're going to go through the curve bit by bit, starting with the origin. Now, the reason why the particles cannot have 0 energy is because if there were no energy, then they wouldn't be moving at all. So they'd be at absolute 0, which is impossible to obtain. But in the exam, you'd be expected to know the reason why the curve goes through the origin is because no particle has 0 energy. Right, the most probable energy is right at the very, very peak of the curve. Now what this is showing you is that more particles in the system have this energy than any other, and that's why it's shown as the highest point on the curve. And average energy is just after the peak. Now the graph is showing it to be around about this area. The average energy is exactly what it says on the tin. This is the average energy, and if you look and drew that dashed line in, the area on the right hand side of the dashed line and the area on the left hand side of the dashed line would be identical, and that is the average energy of the particles in the system. Fourth part you need to know is the area under the curve. Now the area under the curve is proportional to the number of particles in the sample. If you had more particles in the sample, you would basically create a bigger area under that curve to represent that. And then our fifth thing is the activation energy. Now EA is shown on the graph as being roughly the point at which 10% of the particles are sort of above it. So you wouldn't put an EA over here where the mouse cursor is now, because by doing that you're saying that the vast majority of particles have an energy above EA, and that's not really strictly true. What happens is you roughly have around about 10% of particles have energy above EA, but that's dependent on the reaction and of course dependent on the temperature. If you up the temperature of this vessel to 3000 Kelvin, then a significant number of particles would end up with an energy above EA. But generally you label EA towards the right hand side of the curve. And then finally, asymptote or asymptotic is basically a mathematical phrase that says that the curve does not touch the x-axis at any point. And in the exam you could be asked, why doesn't the curve touch the x-axis? And the answer that you would give is because there are always particles with very high energy, so there's no maximum energy given on your graph or your Boltzmann curve. Right, okay, so we need to look at the effect of temperature on the Boltzmann distribution. Now if you can sort of cast your eyes at the blue line on screen, you can see this is a standard Maxwell-Boltzmann distribution curve that's been drawn by the PowerPoint. Now if we want to increase the temperature or decrease the temperature, then there very, very subtle changes will happen. Now we start by increasing the temperature. There's two very, very notable things that happen when you increase temperature. Number one, the curve peak gets lower, so it drops down, and also it sort of shifts to the right. So now the most probable energy has shifted to the right by quite a large amount, because you've given the particles more energy. As a result of that, the energy of the system is shown to increase by drifting the curve to the right hand side. The area under both of those curves would be the same, because the same number of particles are present in both. And that's just shown here. The number of particles remains constant, so the area under both of those curves is the same. Now, looking at EA, this is a significant one. If you take the red curve, the number of particles with an energy above EA is significantly higher than it is in the blue curve. And as a result of that, you're going to have a higher rate of reaction in the red scenario, because the particles have more energy, they collide more often, and they collide with more force, and more of those collisions as a result of that will have energy above EA, so the rate will be higher in that scenario with a higher temperature. Right, so here we've got the two scenarios summarised. You've got red, higher temperature, blue, lower temperature, and you'd be expected to be able to draw a curve for a Maxwell-Boltzmann distribution. You'd be expected to label the axes, and then you could be asked to draw a curve at lower temperature or a curve at higher temperature. I just want to take a moment to just go through that. If you imagine you've been given the red curve in the exam and you're asked to draw a lower temperature, then you would make sure that the curve is higher and to the left, and then when it comes through it must only cross once. So when you draw the curve, it must only cut through the other curve once. If it come down like the blue one does and then comes back out, you'd lose credit for that, you wouldn't get the mark. And then in the scenario for the higher temperature one, if you imagine that you've been given the blue curve in the exam and you're asked to draw a curve at higher temperature, then the red one would be adequate. You would show it going up, sort of drift, the height of the curve will be slightly lower, but it will be drifted to the right, and again it will only cross the previous curve once and then track above it all the way down to the end. It will never ever cut through the blue curve again. Right, so when the temperature increases, the most probable energy of the particles in a sample will increase. When the temperature increases, the number of particles with the most probable energy will decrease. Now that's quite important, because the number of particles with the most probable energy, as we could see from the red curve, was lower. The peak sort of drops, so you haven't got a large number of particles with the most probable energy like you had in the blue curve. Right, when the temperature increases, the average energy of the particles in the sample will increase. Then when the temperature increases, the number of particles with the average energy will decrease. And then when the temperature increases, the area under the Maxwell-Boltzmann distribution curve will remain the same. Why? Because the same number of particles in the system. When the temperature increases, the activation energy stays the same. The temperature doesn't actually lower the activation energy, it just pushes more particles above that energy, so therefore there's a greater rate of reaction. And then finally, when the temperature increases, the number of particles in a sample that have at least the activation energy will be increased.